Dr. D here, and today we're going to learn about a way to measure acid and base strength. That's right, I'm talking about pH and pKa. We're going to go through some definitions, calculations, and examples. So let's dive into it in Content with Content. So to start things off, we're going to talk a little bit about water. So for water, it can undergo a reaction where it forms hydronium ion, H3O+, and hydroxide ion, OH-. And with this, we can actually see that it has a equilibrium constant at 25 degrees Celsius to be 1 times 10 to the negative 14. And this one is so special, it actually gets its own designation of Kw, or the equilibrium constant of water. And so we can solve for Kw to be our products over reactants, where we'll have our concentration of H3O plus times our concentration of OH minus. And you need to keep in mind for all equilibrium constants, you don't do it for pure solids and pure liquids because their densities are known and it's already built into the equilibrium constant value. So for this, we know that our concentrations of H3O plus and concentration of OH minus are going to be equal to one another. And so we'll just put in a variable of x for each. So we can do x times x to give us x squared. Then we can plug in our value of Kw of 10 to the negative 14, take the square root, and we'll find that our x, or concentrations of H3O plus and OH minus, are equal to 10 to the negative 7. So now that we know our concentration of H3O plus and OH minus to be 10 to the negative 7, we can actually solve for something that's called pH. Now pH stands for, the P stands for negative log, and the H stands for concentration of H plus or H3O plus. So we can go ahead and plug in that value of 10 to the negative 7. And if you ever take the log of 10 raised to the anything, you will get whatever that was, because log is base 10. And so taking log of 10 to the negative 7, we get negative 7. And so now we can take the negative of negative 7, and we'll end up with a pH of 7. And so pH is a good way to kind of figure out the strength of your acid or base. So we have a pH of 7 for water, and we can put on this pH scale, where we know that water doesn't cause any stinging or cause our hand to melt off or anything when we dip our hand in it. So it is considered to be neutral. So it's pH of 7, so if anything at pH of 7, it is neutral. If we go down into lower values, that means it's going to become more and more acidic. So we can get down to the lower values and it'll be considered very acidic, such as stomach acid with a pH of 1. If we go above 7, that means it's becoming more and more basic. And we go up to the higher values, meaning that we'll have a very strong base, such as bleach with a pH of 13. So there's another way we can kind of look at this as well. We can actually look at POH, where the P in POH stands for negative log. So whenever you see that P, it always means negative log. And the OH stands for the concentration of hydroxide ion, or OH minus. And so we can go ahead and plug in our value here of 10 to the negative 7 for a concentration of OH minus. We can take the negative log of that, and we'll end up with a POH of 7. Now there's actually a relationship between pH and POH. If we look at this for water, we can see that our pH plus POH equaled 14. And this actually holds true always. So if you ever want to convert from pH to POH, you can just do 14 minus the pH to find your POH value. So let's go through an example. Let's say that we're given our concentration of OH minus to be 0.20 molar. And we're asked to find the pH and the POH. Well, to do this, I would say let's go ahead and start off with the easier one. We know the concentration of the hydroxide ion, so let's find the POH first. So for POH, it's going to be our negative log of our hydroxide ion. Plug in that 0.2, and we'll find out that the POH is equal to 0.70. Now for pH, it's going to be a little bit harder because now we have to figure out the concentration of H3O+. So it's going to be the negative log of our concentration of H3O+. And to find that, we can actually plug it into our equilibrium constant for water, where we have Kw is equal to our concentration of H3O+ times our concentration of OH-. We can plug in the values that we know, and then we can actually solve for H3O+. So we'll do 10 to the minus 14 divided by 0.2, and we'll find that it's 5 times 10 to the negative 14. So now we can take the negative log of 5 times 10 to the negative 14, and we'll see that we have a pH of 13.3. Now another way to do that is to use that other equation we just talked about, where our pH plus POH is equal to 14. We can rearrange this a little bit, so we can see that our pH is equal to 14 minus our POH. So we'll just do 14 minus 0.7, and we'll get the same value of 13.3 for our pH. So either way works. It just depends on which way you like to think of it. So let's talk a little bit about our equilibrium constant of an acidic reaction. So we have Ka. And so Ka is the equilibrium constant for this generic reaction. It's always this format where we have our acid plus water is going to yield H3O plus the conjugate base. It always follows this format. Now, if we have a strong acid, then it is considered to fully dissociate, and it only goes through and makes product. And so the reaction is only going one way. And so let's do an example with a strong acid. Let's say we have 1.00 molar HI. All right, we're going to say it fully dissociates. So we're going to have HI plus water forms H3O plus I minus, its conjugate base. And our concentration of H3O plus is simply going to be the same as our concentration of strong acid. So it's going to be 1 molar, and so we'll take the negative log of 1, and we'll have a pH of 0. So keeping this in mind, that for a strong acid, if we have 1 molar of a strong acid, our pH is going to be 0. But what happens if we have a weak acid? Well, we have the same formula here, but now we have both the forward and reverse reaction occurring. So now we do have to take into account our Ka value. So for our equilibrium constant of this acid equation, it's going to be products over reactants. So we'll have our concentration of H3O plus times the concentration of the conjugate base divided by the concentration of our acid. So let's do an example here. Let's say we have 1.00 molar of hydrofluoric acid. It has a Ka value of 7.2 times 10 to the negative 4. So now we can go ahead and plug this in, where our Ka is going to be equal to our concentration of H3O plus times concentration of our conjugate base, which is F minus in this case, divided by our concentration of our acid, HF in this case. And we can go through and know that our concentration of H3O plus and F minus are essentially related to how much HF reacts. And we'll say that that change is by a factor of x. So for Ka, we'll have 7.2 times 10 to the negative 4, and that's going to be equal to our concentration of H3O plus, which will be x plus 10 to the minus 7 coming from the water, times our concentration of F minus, which we're saying is just going to be how much HF reacts. So we're going to label that as x, divided by our concentration of HF, which is 1 minus x. We can go through and solve for x, and then plug it into x plus 10 to the minus 7, and we'll end up with 0.026475 molar. So then we can solve for our pH, where we'll take the negative log of it, and we'll find that our pH is 1.576. So if we have a 1 molar of a strong acid, we'll have a pH of 0. If we have 1 molar of a weak acid, now we have to consider the Ka value of that acid, and we'll find that the pH value is going to be a little bit higher value. So it's going to be less acidic. All right. So another way to refer to this is with pKa, and this will make our numbers a little bit nicer, so to speak. So for pKa, our P stands for negative log, like it always does, and Ka will stand for our equilibrium constant of our acid. So if we want to find the pKa of HF, it's going to be our negative log of 7.2 times 10 to the negative 4. We can go ahead and calculate that out, and we'll get a pKa value of 3.14. So kind of the real reason for taking the negative log of all these things is to just make them a little bit nicer values. So you don't have to say times 10 to the negative 4. All right, so if you have really, really small values, it'll still get into a rough range of 0 to 14. All right, so we can look at a list of pKa values. Now, the 0 to 14 range isn't really set in stone by any means. We can go much less than 0, as you can see here, and we can go much higher than 14. All right, so as we go down to lower and lower pKa values, that means we have stronger and stronger acids. As our pKa value goes higher, then that means we're going to have a weaker acid. And the inverse is true for the conjugate bases. All right, if we have a really, really low pKa value, and then we're using the conjugate base, that means it's going to be a really weak base. If we have a really, really high pKa value, and we're looking at the conjugate base, that means it's going to be a very, very strong base. So we can also look at a basic reaction where we have Kb as our equilibrium constant. So if we have a strong base, we're going to follow the general formula of our base plus water is going to yield our OH minus plus our conjugate acid. All right. And again, for strong bases, this fully dissociates, so we're just going to do it's just a forward reaction. If we have a weak base, this is where we have to actually consider our Kb value because we have both the forward and reverse reaction occurring. And so our Kb is going to be equal to our concentration of OH minus times the concentration of our conjugate acid divided by the concentration of our conjugate, or divided by the concentration of our base. And so there's a little relation we can have between Ka and Kb, where let's say we have Ka times Kb, we can plug in our products over reactants for each, multiply those out, and we'll end up with something like this. And we'll notice that we have our acid, concentration of acid both on top and bottom, so we can actually cancel that out. And we'll see that our concentration of base can cancel out with our concentration of base. And we'll be left with our concentration of H3O plus times our concentration of OH minus, which might look somewhat familiar because that's just Kw. And so we can have the relation of our equilibrium constant of our acid times our equilibrium constant of our base reaction is equal to Kw. So Kb times Ka is Kw. And in a similar note, we can say that our pKa plus pKb is equal to 14. And again, this comes from Kw being 10 to the negative 14. So if we take the negative log of that, that just gives us 14. That's where that 14 value comes from. Well, that's all I have for you today. So hopefully you realize a little bit on how you can measure acid and base strength with pH and pKa, and why we use P, the negative log of things. It just makes the numbers a little bit nicer to say. So, as always, keep thinking, and I'll see you next time. Goodbye!